Hello, it's David. Bit of a tangent today. Running around the main window in my living room is a string of 80 incandescent bulb fairy lights, which we basically have on all year as sort of background illumination for when we're watching the telly or what have you. And I think they're 0.3 watts each, so that's burning sort of 20 odd watts of power half the day. So I thought it's time to bite the bullet and replace them with some LED versions. Now these are meant to be warm white LEDs. There's 80, so it should be roughly a similar string length, and this requires 3 AAA batteries, although what I propose to do is to replace the AAA battery pack with a USB or similar 5 volt power source. So let's take these out and just see how they look in their intended configuration with 3 AAA batteries, and we'll measure the current consumption and see then how we'll go about matching that up with a USB source. So this is the contents of the box. I think this is fairly standard, a whole string of, I presume, parallel wired LEDs. Otherwise, only one failing, the entire lot would, or failing open at least, the entire lot would be dead. But also 80 LED drops in a row would not be powerable by a set of 3 AAAs, because that would be something in the region of 120 volt drop, so that wouldn't work at all. And in this box here we can see we've got a simple switch. We've got the 3 AA cell holders. We've got a simple switch, and we've got a resistor in there that looks like red, black, black. Mumble. Anyway, it doesn't matter. That's just the percentage. So red, black, black. What's that? That's 300. Is that? So is that a 30 ohm? Let's have a measure of that. I don't have. My resistor chart knowledge is pretty weak. Hold on, wait a minute. I've actually got a chart here. 2. Red is 2. So 2, 0 times 10, 0. So yeah. So I think that's a 20 ohm dropper resistor. So let's see what sort of current we have flowing through this. 3 freshly charged AA cells here, which I shall pop in. That's actually quite nice. Yes, that is a warm white. Can't say that is lying to me. Let's power some of these lights off. There we go. Actually, that's not at all bad. Let's switch the lights back on and do some measurements. The lights are back on, and let's just do a simple voltage measurement for the first point here. So let's go from the top of this this cell here to the tail of this cell here. There we go. So we're reading 4.37 volts. Call it 4.5. Close enough for government work. And let's pop the cells out of there. Obviously these are, I assume these are nickel metal hydride. Yep, nickel metal hydride batteries here, cells I should say. So the voltage will vary slightly, but even with alkaline, I think that's going to be 4.5, pretty much. What's our resistor reading? I'm hoping that is, as I have successfully, as I have deduced it. Yeah, there we go. So a 20 ohm dropper resistor. So is there a simple way for me to measure the in series current here? Well, I'm not seeing any lights. Really? Switch the amp. Oh. Oh, I'm such a silly sausage. Yes, I will need to actually put it into milliamp mode. That will, oh sorry, milliamp, the milliamp port. That would probably have a significant effect on whether it would work. It does not have a significant effect on whether it would work. Put the switch on. There we go. We've got a lovely glow, and we're pulling 63 milliamps. So we've got 4.5 volts at 63 milliamps. So that is roughly a third, between a quarter and a third of a watt dissipated, which is the same total as one of the incandescent filaments that I have running at the moment in our house. So this would be a 80 times saving, if you like. But I want to fit a USB style charger in here, and perhaps I don't even need it to be that bright. So I think what we'll do is we'll cut this connector off, and we'll start looking at what we can do with the power supply here. I think the obvious thing to do is we'll connect it up to a bench power supply, and we will limit it to 60 milliamps, and then we'll just vary our current cutoff a little bit and see what achieves a nice gentle background glow. Okay, so we've got the cheap Chinese power supply out. We've got our LED strip hooked up here with croc clips, and we've got this set to go at 5.1 volts upper limit and 0.06, which is 60 milliamps current limit. So let's throw the switch, and from what we saw before, that should produce a nice warm and relatively bright glow. There we go, look at that, lovely. So that is current limiting. That only requires 2.8 volts to generate that 60 milliamps. But there we go, that looks nice. So what can we drop that current down to and achieve an effect that we like the look of? I suppose the thing to do here would be to turn off the lights. Okay, so lights have been dimmed, and I've got a one LED monitor panel on behind me here, just to simulate sitting at home watching the TV at night. And these are actually really quite bright at 60 milliamps. So let's slowly wind that down and find a current that produces a nice background glow. So we're dropping. Probably somewhere around there is not bad. That's 10 milliamps, that's very low. So I would say something between 10 and 20 milliamps. That's 20 milliamps. That's 15 milliamps. That's halfway. Was 13 that's showing. So that's halfway between the two. So between 10 and 20 milliamps seems to be a good current. Let's just pop the multimeter in line and make sure that current reading is accurate, because these cheap meters, cheap power supplies, can be quite some way off, to be honest, at the lower limits. There we go, and 16.7. That says 13, 14. You see that the percentage accuracy is not good down here. So about 15, 16 milliamps is not bad. That produces a pretty nice glow. So I think it's time for a bit of maths. So with a nominal 5 volts and a desired output of about 15 milliamps, that gives us about 330 ohm resistor required to drop that. However, that's not strictly all that's going on. We have a voltage drop across these LEDs on account of them being LEDs. So maybe we ought to measure that. So that may factor into our calculations. So I'm going to reuse the same what's it called, crocodile clips here, and we'll just put this into resistance mode. And we'll put it into LED test mode. There we go. And we're seeing, look, a forward voltage drop of 2.5 volts. So it could be that we actually need half that 330 value. So potentially something in the 180, 150 region to get that drop. So why don't we connect up our power supply now at 5 volts, but put our decade resistance box in series to get ourselves a measurement. So I've called it a decade resistance box, but actually it's a decade resistance board. I've got it set up for 330 ohms, and we're going to put it in line here with the LED strip. What we'll do is we're going to set our compliance voltage again to 5.1. That's absolutely fine. But what we'll do is we'll now change the compliance current, the maximum current allowed, up to that 60 milliamps, so that we won't blow it if I've massively undercalculated here. So 5 volts comes out here, goes through the resistance box, goes through the LED strip and returns. This should be fine. Let's turn it on. There we go, we've got a lovely glow, and we're not measuring any amps at all. Now that's possibly because of that factor of 2 that I haven't taken into account here. This is 5.1 volts, but there's 2.5 volts dropped across here. So we could be talking about only being 2.5 volts across this decade resistance box, which means that we would need to halve the resistance to maintain that 15 milliamp target amount. So let's just measure the voltage across the resistor. I'm expecting it to be 2.5. There we go. Yep, just under 2.5 volts. Sorry. So we're just under 2.5 volts across here. We need to halve our resistance. So the way I'm going to do that is to instead bring this down to 180 to start with, and we may drop again even lower to 150. Yep, that's only showing 9 milliamps. Now 13 was kind of what it was showing when we got our target last time. So let's take that down to 150. There we go. Look at that. 150, and we're showing 12. I think that that's going to be pretty good.
I'd like to thank this video's sponsor and the supplier of my project PCBs, PCBWay. PCBWay aren't just about PCBs either, although they are extremely good at that. They also offer component assembly, CNC machining, 3D printing, and a variety of other manufacturing services. They have a number of community-focused offerings too. The Shared Project Hub is an open platform for makers to share and exchange their ideas, and the PCBWay store is a great place to pick up assembled modules. I mean, who wouldn't want a musical Tesla coil? So many thanks again to PCBWay, and I recommend you have a look at some of the links included down below.
Okay, so here's the plan. I've got myself a couple of old broken iPhone cables. You can see they're basically held together with tape and heat shrink. But hopefully the actual USB-A connector is fine, so we can cut these part way through, find the +5 and ground, fit a switch in line. This is a big 240 volt switch, but the point is it'll give me a bit of space, hopefully. Then I can squeeze my 150 ohm resistor in there as well. So first things first, let's see what's going on inside the switch case. Oh gosh. Screw terminals. These are obviously intended for 240 volt 3 amp wires. That is not going to be ideal for the very, very tiny wires that we have in our LED strip and indeed in here. So it could be that we are going to be soldering to those anyway, if these will take solder without melting everything around it. So that would probably be my first step, but I think there's going to be plenty of room to squeeze a resistor in there as well. Right, so first things first, let's cut open this lightning charger. Let's see what we've got inside. Shielding, not going to be much use to us. And there will be, I suspect, 4 cores. There are many cores, but I think most of them are probably just shielding. So we've got ourselves red, green, white, and shielding. So perhaps the shielding is the ground. This is going to be quite awkward to work with. Separate these out a bit so that we can get the it could be actually that a lot of that is just fibre, nylon fibre or something similar that is simply there for strength. Would not surprise me. Let's bring in our multimeter again and we will check what we've got going on. Right, so I'm going to be relatively confident that red is positive, so let's put our crop clip onto that. Then I'm going to probe around with the other end looking for the ground. Now I've got a little USB power tester here, which I'm hoping will provide a degree of current limiting in the event that I short something out. So I'm going to put that in series, and I'm going to bring in a USB extension to help me, just a USB-A extension lead to help me power the LEDs. I have a 5-volt supply up there, but I'm not 100% convinced that was working, so we'll see actually on the USB tester first whether we have any juice. 5.2 volts. Okay, so with our positive connected, what I assume is positive, let's try. There we go, 5.2 volts with the strand and also the shield, but that might just be because they're shorting out there. So, okay, shield to red wire. Okay, so I've stripped this back a little bit more. I'm just going to do a bit of continuity testing here. So we've got the meter in the background here in continuity mode. No, we haven't. Now we have continuity mode. Right, so this is connected to there. It's connected to there. It's connected to there. So these, to me, all seem to be ground. Now, I'm not sure whether those are individual strands. Sorry, I'm showing that up there. Not sure whether those are all individual strands or whether they've just been separated when I've clipped it out. We should not have continuity to the 5-volt line. No, we don't. So I think what we can do is to weave these all together. And if this will take solder, I'll tin those up, and that will be our ground line. They feel like fibre, but they are conductive. It really is very, very fine stuff. Let's see if we can tin them. Start back here where it's better wound, I think. There we go. Yep, that's taking a bit of solder. So I'm going to run down here and I'll obviously just cut it short where the tinning has worked well. So see, it's diverging there at the end. That's fine. We've got to put a resistor in here, so we'll cut that off, and there we go. We should have our 5-volt and ground. Let's take that screw out and see whether that will take any solder. That's the let's turn my soldering iron up to 350, because that's going to need a bit of punch, I think, to solder to this big old screw terminal. That's not a that's a squeeze style terminal. Maybe we just do run straight in there. That one will squeeze in there quite happily. So maybe I'll strip this one back a bit further actually, and we squeeze this as well, and we look to do the resistor on the far end. Can I do this without ruining it? Yes. Okay, so we're low side switching, but I can live with that. That stuff might short out to there, but that's fine. That is the negative side. The positive side has a nice long wire, and that is over by itself. So I think that should be fine. Then in terms of the LED strip, I can't remember which way around the wires were here. I've got a longer one and a shorter one. So I'm going to put the LED tester back on. There we go. Back on the chain. So the longer wire is the anode, or the positive side. Okay, so I'm now going to introduce my 150 ohm resistor. I think what I'm going to do is I'm going to basically double back. So mount the resistor anti-parallel. And then fold that round again to provide something to connect to. It just uses up a bit less space. We'll see here, it might not work. No harm in giving it a go. And I've seen how that's flowed poorly. I'm going to dob some solder on there. And we'll just douse it and see what happens. Okay, that wasn't too bad. Although I am going to have to clean all of that flux off now. Right. Trim that end off. And we'll get some heat shrink over that as well. So this will come back out the other side of the heat shrink, and that will give me something to mount to. That's my initial plan. Sorry, I managed to do that off camera. There we go. That's heat shrunk and protected. I'm worried about the structural integrity of this. If things are just hanging on the wires themselves, that's not going to work. But the way that this works is it's got these sort of little strain relief clamps here, and they've got to squeeze down on something. And the only issue is if it squeezes down on my resistor, I suppose. So let's see how we can squeeze this in here. So that would go in there, that would bend around like that. That's fine. That doesn't squeeze on my resistor. Whether it squeezes on anything at all is the question mark. Then we're going to have this anode, which I'm covering completely with my hand. coming down here, and we need to get that in here and into the common side. Let's get rid of that excess solder mask there. Not solder mask, heat shrink there. A bit of a squeeze. That's not quite correct, I think, at this end. So yeah, that maybe that little loop around there is not helping. Bend that down a bit more. My resistor maybe has taken up a bit too much space. This third one here might be impacting on that resistor. I may need to trim that back a bit, if I can. Let's cut in like that, then like that. Try and flex them down out of the way. Like that. And that may be sufficient, or that might actually just give and break. No, that's still touching somewhere. Ah, no, there we go. Look, my wire, that's it. I'm squeezing that wire. Can you see that? There's a screw hole there, and my wire is going straight across it. Whoops. Might be possible. That side's now happy, and it's that one that's unhappy. So the problem is basically that these screw terminal pegs here needs to make flush contact down there, and it's a little bit chaotic at the minute because I've got one wire that's longer than the other, which I thought was me giving myself options, but it's proving problematic. How about that? Yes, there we go. We're in. Right, I'll bring the tester back in. Take that for a wider view. So the tester's back in shot, although upside down, and we're going to throw the switch. Lovely, lovely bit of illumination. And yeah, just have to hope that those bits of strain relief inside the switch here are sufficient to take the load. And we'll be using, well, it'll tell me here. The consumption is oscillating between 10 milliwatts and, well, it's now settled at 10 milliwatts. So the power consumption of these is absolutely minuscule and less than one of the little bulbs that I'm replacing them with. Fairly simple project, but I thought it was worth sharing. Thanks for watching. Catch you next time.